All right, in this video, I am going to be introducing solving problems for objects that are in freefall. So first, let's just kind of go over what that means if an object's in freefall. Well, that means that its initial velocity is always going to be 0 meters per second, right? We're just about to drop an object. And in this case, maybe the height, well, I don't really know my height in this case. Actually, that's what we're going to end up trying to solve for. But on a graph, since I'm dropping it from some height, I could put my position over here on my position versus time graph. All right. Just before it hits the ground, in this case, I don't know my velocity just yet, but the only force that's acting on my object is the force of gravity, and whenever that's the case, my acceleration due to gravity, I can almost put AG right here, is negative 9.8 meters per second squared. And the negative, again, means that acceleration is going down, and that kind of makes sense because, again, the only force acting on my object is my force of gravity, so my net force has to be going down, which means my acceleration is going down. All right, in terms of hitting the ground, it's just before it hits the ground, all right, and so we could almost round down and say that the position at the very end is 0. All right, so let's look at motion maps. All right, remember the only force acting on our object is the force of gravity, which means my acceleration is pointing down as well. Right? And if my object starts at rest, that means that it's going to start to increase speed as it falls to the ground. So I should have my velocity arrows getting bigger and bigger as my object goes down. Right? And then what's causing that again is my acceleration. Maybe I could put a little bit of an arrow here. And then my acceleration arrows, I usually just make a little bit thicker. And I remember I always kind of make my acceleration arrows the exact same length. The acceleration's constant. It's the constant acceleration that's causing an increase in velocity because both of those are going in the same direction. All right, so let's calculate. It says hang time right here. Let's calculate the free fall for an object. And in class, what we ended up doing is we dropped our object from the ledge of that second story on top of the point. So if we were to make a graph, by the way, as time increases, the distance covered per unit time is going to increase, or in other words, that I'm going to be increasing speed, so my slope needs to be increasing speed as well. All right, for velocity versus time graph, remember that as I get further from the x-axis, I'm increasing speed. My object starts at rest, so I know I have to start here at the origin, but the question is, do I go up here or do I go up here? Well, I'm going in the negative direction. Right, so that means that I need to be in the negative quadrant. All my velocity values here need to be negative. All right, so those are my graphs. Now let's actually solve for free fall. And remember, what we ended up doing is we dropped a tennis ball from a ledge at the point, and our goal is to figure out how high is the ledge at the point. And this is, by the way, just above the stairs. So if that's the question I'm asking, then what I'm looking for is this change in distance, right? And that change in distance is always going to be delta x. So that's what I'm looking for. All right. So in terms of solving this, what I want to challenge you to do is to think about the equations. You could pause the video and look at all the equations that we have. And I want you to maybe try to solve this or think about how you might solve this, maybe even just for about a minute or two, as best as you can, because you have all the tools already to solve these problems. There's really nothing new that I'm going to be going over at this point. All right. So if I am solving this, all right, first thing I need to do is I need to kind of choose what equation I might use. And actually, before I do that, let's look at some of the things that I know. I know that my initial velocity is 0 meters per second. I know that as the object's falling, the acceleration due to gravity is going to be negative 9.8 meters per second squared. Okay, that seems like all I know right now. All right, if I look at my equations, again, what I'm looking for is delta x. So let's see, this equation has it, and this equation has it. None of my force equations or my energy equations have delta x, so it's either going to be this one or this one. So then I have to ask my question: Am I changing velocity or changing velocity or going at a constant velocity? My object's definitely increasing speed, so it's definitely changing velocity. So this is my equation just for constant velocity. This has acceleration, so it's definitely changing velocity. This is going to be the equation that I end up using. All right, so delta x is equal to 1/2 at squared plus initial velocity times time. Right? And now it's just a plug and chug to find my distance. All right, 1/2 acceleration is negative 9.8 meters per second squared times the time. Oh, so I don't know time yet. Right? And I need that to solve my distance. Right? What we ended up doing in class is we dropped the tennis ball from the ledge, and we used a slow motion capture to actually figure out how long it took for the ball to fall. And it took 0.97 seconds, about. So that's the time we're going to put in. And again, you had to be in class to get that number. 0.97 seconds squared plus my initial velocity, which is 0. So I could put in a 0.97 here, but it doesn't matter because that 0 is going to cancel out over there. All right, so when I do 0.97 squared times negative 9.8 times 0.5, what I get my distance to end up being is negative 4.61 meters. All right. And does this make sense that I have a negative answer for distance? Absolutely. I started here and I went in the negative direction. So my distance covered was in the negative direction. I should get a negative answer. All right. So the next thing we're going to try to solve, and by the way, we could fill this in over here. I guess it doesn't give us that, but I could put in delta x, or maybe in between. Delta x is equal to negative 4.61 meters. All right. The other thing that I want to solve in this problem is, so if I were to put an x here, I could put 4.61, and that would be positive because it's just a position. Change in x is your distance covered, going from here to here. All right. Now the other thing I want to solve for is maybe the velocity just before it hits the ground. All right. And so what I'm going to do is I'm going to just go back to the equations I've been using all year, and looking at these, I can't use my constant velocity equations. None of these have final velocity in it. These are my changing velocity equations, and it's really this one that has final velocity, so I'm going to use this one right here. So velocity is equal to at plus initial velocity. All right. Velocity is equal to negative 9.8 meters per second squared. My time, I just put in 0.97 like before. Initial velocity is 0. And when you do the math on this, you get your velocity to be negative 9.506 meters per second because it's velocity. And again, the negative, I don't need to put the arrow if I have a negative, but the arrow always helps to just kind of reiterate that velocity is going downwards. All right, and that's it. That's free fall. Notice that, yeah, it's a new situation, but for the most part, it's really just using what you've already learned and applying it to a new situation. Thanks for watching.